Welcome back to ECE 207. We have an aggressive agenda for today. I'm not sure if we will get all the way through it, but it is required for the homework problems. I may jump out of Thevenin-Norton equivalence and get into superposition and Wheatstone bridge and then come back to Thevenin-Norton equivalence halfway through that discussion. We'll start with finishing up the mesh analysis example that we barely started last time. I'll see how well you can do that with a class participation exercise. And then we'll get into these wrinkle cases where the mesh analysis is going to be impeded or maybe a wrinkle introduced because of a current source being present in the mesh problem. Then we'll go into the last three topics. Let's begin. With the example that we started last time. I hope it is clear that that looks like three window panes or meshes, and that's what we're going to then use to say, well, it looks like there's more nodes than there are meshes, and because of that it might be to our advantage to actually do mesh analysis if all of these are valid meshes. Here's, let's say, I1, I sub 2, and I sub 3. Then we would have three unknowns, the I sub 1, I sub 2, and I sub 3, instead of having to worry about all of these different nodes that we might encounter if we tried to do nodal analysis on this particular problem. There are quite a few nodes there, and that would then result in a higher dimensional problem to solve in terms of finding currents and voltages in that system. Let's then start by, since we have mesh currents, we are actually going to do KVL equations. Let's say we'll write the first one obviously with mesh number 1, KVL around mesh 1. Here we're just going to be summing up the voltage drops in the direction of that mesh current. And in this case we're going with mesh 1, and so I1 is always going to be positive as we move around that loop or mesh. We're going into the minus terminal of the first voltage source. That's going to be minus V sub A. Then we have a voltage drop from left to right in the direction of positive current flow I sub 1 across resistor R sub 1. That voltage drop is given by Ohm's law, which is R sub 1, I sub 1. Then we're coming vertically down through R sub 2, and Ohm's law says we need to have the resistor R sub 2 times the current going down from top to bottom. What we've identified, though, with our mesh currents is there's two currents involved. There's two mesh currents involved in that current going down. I1 is going down. It's helping the current going down, meaning the net current going from top to bottom, if we want that voltage to be labeled plus to minus from top to bottom, we say, oh, we have I sub 1 minus I sub 2. That's the current going down through that resistor in the positive sense. I1 is down, I2 is up. I2 is impeding or going against the direction we want to go. That's why it has the minus sign. Then we need to keep summing drops. That R sub 3 presents a drop as we go from right to left across the bottom, and there's only one mesh current going through R sub 3, and that's I sub 1, and there's our first equation of the three equations that we're trying to write or find. That's KVL around mesh 1. Questions on that? Let's look at KVL around mesh 2. And let's see if I have this working. There is our circuit again, so that now instead of scrolling, I'm actually going to just switch to a different screen or a different window, and hopefully that will be less difficult for my little computer. I want to be nice to it. Let's start at this location and walk our way around. I just like playing that particular direction. Now you have to bring a highlighter to lecture. 4-color pencil and a highlighter. That's the direction I'm going to go in terms of writing my next KVL equation. I'm going to go clockwise, starting in the lower left-hand corner with mesh number 2. I'm going to have a voltage drop across R sub 2, but now it's going to be relative to going from bottom to top. If I want a positive voltage drop across R sub 2 from bottom to top, now I sub 2 is going in the positive direction that I'm headed. I sub 1 is going against. Meaning, now if I write that equation, KVL around mesh 2, it's going to be R sub 2 times I sub 2 minus I sub 1 plus R sub 4. What current goes through R sub 4, or how many currents go through R sub 4? Just the one, I sub 2. That drop is going to be then I sub 4, I sub 2. What happens as I go past or through that voltage source? It will be a voltage which depends on how I enter that source. In this case, I'm entering it through the negative terminal first. It's going to be minus V sub B, because I'm really summing voltage drops. This is actually a voltage rise. That's why it gets a negative sign, is another way of thinking of it. But I would just say, which terminal am I entering first? Let me write that sign down. And finally, I have the voltage dropped across R sub 5, and that's in the same direction from right to left that I sub 2 is going. And there's my second equation of the 3 equations that I want to write. Questions on that? Then I have the last equation, KVL at 3. Now I have a voltage source to worry about and one resistor. There's only one current going through that resistor. That voltage drop should be easy from top to bottom. That will be R sub 6 times I sub 3. If I'm now moving around that particular mesh in the same direction as the previous two, I'm going into the positive terminal of V sub B. I now have plus V sub B plus R sub 6 I sub 3 as my last equation, KVL around mesh 3. It's going to then be plus V sub B plus R sub 6 I sub 3 equaling 0. Questions on those 3 equations? And that is enough information then to solve for the 3 unknowns, I sub 1, I sub 2, and I sub 3. Once you have those currents, you can solve for anything you want in that circuit. If somebody asks you for the power absorbed in resistor R sub 2, how would you do that problem? What was the answer, or one of the Suggestions? Okay, we want the net current flowing through R sub 2. And actually, with R positive resistors, it doesn't matter if we assume the current is going down or up. We just need to assign one and work from that. In this case, if we said, let's make our current go down, let's say it's I sub D, then we could say, well, it's R sub 2 I sub D squared. And now we just need to rewrite I sub D in terms of what we've already calculated. I'm assuming we've now calculated or determined I sub 1, I sub 2, and I sub 3. How do we express I sub D in terms of I sub 1 and I sub 2? Does everybody agree it does not involve I sub 3? Because I heard some different, and it really doesn't matter because we're squaring it, but we need to take the difference of I sub 1 and I sub 2. The way I've sketched it, it really should be I sub 1 minus I sub 2 quantity squared. That's the power absorbed by resistor R sub 2. If we've calculated I sub 1 and I sub 2 and I sub 3, we can then find or determine that absorbed power. Do we need to go through how we would write those three equations in standard form? Does everybody get that concept or that process? I didn't hear any objections, so I'm going to assume you know how to do that. That needs to be known by exam number 1. If you now we get a little feedback. All right. Usually that happens. What am I looking for? I'm looking at equations involving I1, I2, I3. Those will all be on the left, equal to whatever ends up left over, and I'll put those terms on the right. And to be consistent, I'm going to have an I1, an I2, and an I3 equal something in all three of my equations. If I look at the first equation, I had, and you could actually see this maybe from, as you study this, you'll start to be able to write these by inspection, actually. If you don't have any dependent sources, it's much easier. But if we now look at what resistors touch mesh 1, or current I sub 1. This resistor touches it, this one touches it, and this one touches it. Those three resistors should be the coefficients in or associated with I sub 1. And if you look at your equation, that's going to indeed be the case. And you can see that R sub 2 is shared between mesh I1 and mesh I2. Does mesh current I1 share any resistors with mesh current I sub 3? No, so we should expect a 0 coefficient for the factor for I sub 3 in the first equation. And V sub A, we see one source. Is that encouraging or discouraging current flow in the direction of I sub 1? If I increase V sub A, will I sub 1 increase or decrease? Increase. So it will be on the right-hand side with a positive sign. Question?
If we're asked to write it in standard form and we don't put 0 and then
Oh, it depends on my mood. The question was, if we're asked to put this in standard form and we do not explicitly write plus 0 I sub 3, will we lose points? After 140 papers, and you are the only one that did it, sure, you'll probably miss 90 points out of 100 on the entire exam. Just because, no, I don't know. But if it's 0 times I sub 3, you're correct, unless I say, please keep all of the currents and the variables in every equation. Then you would be forced to put 0 times I sub 3. But Theoretically, if you leave it out, that would be correct, unless I said put it in matrix form, and then you have to put the I sub 3 there. What did we just say? We said we had an R1, an R2, and an R sub 3 touching I1. Those come in with a positive. We had R sub 2 shared between R1 and R2. I'm sorry, between I sub 1 and I sub 2. R sub 2 then comes into the I sub 2 coefficient with a negative sign, and we said that V sub A should be positive on the right-hand side. And if we go and collect terms from our very first equation, it should be consistent with that expression. If we do the second equation the same way, I'm going to go back and look at my circuit. The three resistors that touch mesh I sub 2 are R sub 2 plus R sub 4 plus R sub 5. R sub 2 is shared with I sub 1 and I sub 2, so that should be a negative R sub 2. And does I sub 2 and I sub 3 share a resistor? No. So again, this one is 0 I sub 3. Is there a source in that particular mesh? If I increase V sub B, is I sub 2 helped or hindered if I make V sub B bigger? I sub 2 is actually coming out of the positive side of V sub B. If I make that more positive, it's going to increase or make I sub 2 better. This should be V sub B on the right with a positive sign. Again, I'm just trying to do this a little differently to write these and then check my work by looking at what I would have obtained had I rewritten my original equations in this form. Question?
Yeah, I'm looking back at the notes, and you had a standard form, but it was for the nodal analysis. Is it different between nodal analysis and mesh analysis?
Yes, the question is the standard form, well, the structure will be the same. It will be your unknowns with coefficients equaling something forcing it on the right-hand side. But the structure is going to be different, because what do we have here? Here we have resistors times currents equaling voltages. Everything here should be a voltage in these equations. What did we have in the nodal analysis? Now we're dealing with KCL equations. Those are all currents, aren't they? It's V's are our unknowns divided by resistors or reciprocals. Those are our currents, or somehow reciprocals of resistors. So that now we have V divided by R. That's a current equaling I's. So the nodal analysis standard form is going to be structurally it's going to be the same. Coefficients, unknown, equals something forcing it. But those are currents. For KVL or for mesh analysis, you're writing KVL equations. Now you're going to be writing voltages. We have one more equation, which is the third equation. I3 does not share any resistors with I1 or I2. We should be expecting then those two coefficients to be negative. We have R sub 6 times I sub 3. And if I increase V sub B, does that impede or does that help or discourage I sub 3? It discourages, so in this case I should have a minus V sub B. And if you look at your third equation the way that we wrote it initially and put it in standard form, you should end up with these three equations. We did it two different ways as a way of checking our work. Questions on that? All right, take out a piece of paper with your code number and show me that you can perform mesh analysis. I'll give you 5 minutes. You have until 5 till 4 to finish this. Shouldn't be that difficult, I hope. And unless you need to, you don't necessarily have to draw the circuit, but sometimes that helps you think about what's going on as you're sketching it. But it shouldn't take you too long to sketch that circuit. I should be quiet. Is everybody finished? We're out of time. Pass those to your right, unless you're on my left. then pass them to your left. You're on my left, this section. You're on my right. How's that? So if you're on my right, pass to your right. If you're on my left, pass to your left. And your code number should be on those papers. Everybody get them? Thank you. Wow. Guess somebody's not. Oh.
Those are my notes.
Oh.
Thanks. There you go.
Is that everybody's? Did somebody help me out and bring them down from the right? I think. Thank you. Did you do this by inspection, or did you write the mesh equations, or both? You could have done it either way. Which way do you want me to work it? Both? We're in a hurry, so yes, we'll do it both. Let me just write it by going KVL around the two different meshes. If we do KVL around 1, we have R sub 1 I1 minus V sub A plus R sub 2 times I1 minus I2 plus V sub B equals 0. Woo! Does that look familiar? Okay, no more papers in. KVL at 2. Now we're going against V sub B, or we're entering the negative terminal. It's minus V sub B plus R sub 2. Now we're leading, so to speak, with I sub 2. We want the positive drop to be from bottom to top. It's now I sub 2 minus I sub 1 plus, was there another resistor up there hiding? R sub 3 I sub 2 plus R sub 4 I sub 2 equaling 0. That's what I was looking for. If you didn't get that, I'm sorry, but hopefully you'll get it by the exam. Let's look at this wrinkle. That's not standard form, but I didn't ask for it to necessarily be in standard form. The question was, is it in standard form? If you put it in standard form, that's fine. That's correct also. So if you go that far, which on an exam I might ask you to do that so it's easier for me to check, so you will want to be able to do it in standard form. I'm just saying if you get it in this form, I'm hoping you can put it in standard form. Question?
For the first portion, it has 2 voltages. How do you write that part? Is that standard? Do you have both voltages in one thing?
So the question is, what do you do with those 2 voltages? Now you have actually 2 independent sources. They could be dependent. In this problem, there are 2 independent sources in the same mesh. Those will just be 2 independent sources, and they will appear on the right-hand side. Their sign on the right-hand side depends on how they are helping or hindering I sub 1. In this case, if they were put on the other side, algebraically, you would just have V sub A minus V sub B. And those would be given sources, whatever those are given to be. Question?
When you're writing standard form, is it always going
Okay, so the question was, if you're writing standard form, could you have voltages and currents on the right-hand side? If we are writing mesh equations, what's on the left? R times I voltage, right? We have, so if it's an equality sign, we have to be compatible. Meaning if you have a voltage on the left, you have to have voltages on the right. If you end up with a current on the right, there's a problem. Does that make sense? And if you're writing nodal analysis or equations involving nodal analysis, then if you're dealing with currents, if you're having currents on the left, you better end up with currents on the right. Everything has to be compatible. Let's look at the wrinkle, which is when we have current sources in the network. And we'll do this via an example. Here's, let's say, V sub A, R sub 1 across the top, then a dependent, what kind of a source is that? Current. It's dependent current source. It's the diamond with a line or an arrow in it. Let's say it's 5V sub 1. Underneath that is another resistor, R sub 2. Then to the right, we have a voltage source, plus minus V sub B, R sub 3, and then vertically down we have R sub 4, and let's say we don't have any resistor in that bottom path. I'm actually not even done specifying the circuit, because if I have a dependent source, you have to be told where is that dependency, or where is V sub 1. In this case, let me define V sub 1 to be plus V sub 1 minus a voltage drop from left to right across R sub 1. The problem would arise if we now define our mesh currents, which this looks like it's begging us to do mesh analysis because I can see two window panes. There's an I sub 1 and an I sub 2. But as you now draw that down, you go, okay, I'm going to be doing KVLs around those two meshes. Wait, what do I do with the voltage drop across the current source? I don't know how to do that. I can't do that because it's not a resistor. If that was a resistor, instead of the dependent current source, I could solve that problem. But now I can't do that. And I have two meshes, and it would be in both meshes. What we want to do then is define this super mesh, which says, you know what, we don't have to necessarily go around the little one. We can go around the big one. And we'll call that M1 for super mesh 1. We'll do KVL around that dashed path. We'll just bypass the drop down that middle vertical drop or collection of elements. Is everybody okay with what I'm trying to do? Then I will have to, how many equations do I've identified two mesh currents. I should end up then with two equations involving those two unknowns, I1 and I sub 2. Now if I just do one super mesh, I have one mesh equation. I need another equation, maybe a constraint equation, that's relating that current source to the unknown currents I sub 1 and I sub 2. Here's what I'm doing. Here's the solution. Because I couldn't do these simple meshes around I sub 1 and I sub 2, I'm going to identify a super mesh that basically goes around or sidesteps the need to define the voltage drop across the current source. And what I have indicated then is that I'm going to write my KVL equation around that supermesh, which I'm defining as M sub 1. And there's my circuit that I had already drawn, and now I have this super mesh that I want to follow around in order to write my voltage drops around that particular circuit. I'm going to start in the lower left-hand corner. I'm going to go through V sub A. I'm hitting minus first. It's minus V sub A. R sub 1, there's only one mesh current associated with that. It's going to be R sub 1, I sub 1. Then I'm going to hit V sub B, the plus sign first. I'll say plus V sub B. Then I will have R sub 3, I sub 2, plus R sub 4, I sub 2, and I'm done. That's going to be my KVL equation. My second equation, because I need two independent equations, my second equation is going to be related to what's happening in that branch that I basically neglected in writing my mesh equation. And in this case, what can I say about 5V sub I? That's a current going up. What does that equal in terms of I sub 1 and I sub 2? Is it I1 minus I2? Which, if I now cranked up one of those currents, which one would help 5V sub 1 become more positive? I2, wouldn't it? So that tells you which one is actually positive. It's going to be I2 minus I sub 1 is equal to 5V sub 1. Is that okay? So let's go back and write our KVL before we forget it. But the KVL now around M sub 1 is going to be minus V sub A plus R sub 1, I sub 1 plus V sub B. Again, we have two voltage sources. We could have two, we could have three. It doesn't really matter. We just have to keep track of those. Plus R sub 3, I sub 2 plus R sub 4, I sub 2 equaling 0. We've used up all of our mesh equation with that super mesh. We decided we couldn't find or write an equation for mesh 1 or mesh 2 in isolation. We had to do this super mesh. Because of that, we need this other equation, or we need another equation. And that other equation is our attempt at trying to express now you need to be paying close attention because it's very important that you switch colors in the middle of that P. That's critical to your understanding of this material. If you're watching, that's a function of how slow my computer, or how hard my computer is trying to catch up with when I switch colors. I'm just so fast with writing, I got into 3 words before it realized it needed to switch colors. Sorry. Thought you needed something to bring you back from your depth of sleep. Variable in terms of the mesh currents. Those are our unknowns. And you'll be bleeding red and blue this weekend anyway, correct? So that's why we're switching halfway between. Sorry. And we said that other equation was our our current source, 5V sub 1. If we can remember, I sub 2 was going in the same direction as the current source, 5V sub 1. This is now I sub 2 minus I sub 1. And this is our second equation. Am I now finished? What do I want with respect to my equations that I'm writing eventually?
Solve them.
You want to solve them, correct. You need to solve your equations. And in order to solve those equations, what do you need to have happen? You need to solve for the variables. And which variables are we solving for? Currents, I sub 1 and I sub 2. What is given in our problem? Whatever our sources were, our independent sources, correct? And we had how many of those? I'm sorry? What was V1 again? I'm trying to get you to see that V1 is something that is not a given, is it? I mean, it was given in your circuit, but it's not an independently given variable, is it? So V sub 1 we need to eliminate in that second equation. We need to get rid of V sub 1. We need to write it in terms of I sub 1, I sub 2, and our sources, our independent sources, maybe, V sub A and V sub B. In this case, V sub 1 is what you just said. It's the voltage drop across R sub 1, and I can write that in terms of I sub 1 and I sub 2 without involving my sources. V sub 1 is R sub 1, I sub 1. Does everybody see that? And now I can get rid of V sub 1, and I'll have two equations in terms of I1, I2, V sub A, and V sub B. V sub 1 will be gone. But I need it initially to write my equations. If we go back, then I need to express this dependent value in terms of I sub 1 and I sub 2. And I think what some of you are seeing, hopefully others see it later, if not now, but V sub 1 in terms of I sub 1 and I sub 2 was simply R sub 1, I sub 1. If V sub 1 happened to be a voltage that shared I1 and I2, you would have to involve both I sub 1 and I sub 2. In this case, V sub 1 was defined to be the voltage dropped across R sub 1. And that now allows us to rewrite this second equation in the following way. We can now say 5 times V sub 1, which is R sub 1, I sub 1, is equal to I sub 2 minus I sub 1. And that's now a second equation that will allow us to complete the problem. If we needed this in standard form, our first equation was, if I go back in my notes, we had what multiplying I sub 1? Simply an R sub 1. What was multiplying I sub 2? That was the sum of R sub 3 and R sub 4. And then we had the two voltage sources, which if we take to the right-hand side would be V sub A minus V sub B. Then we have that second equation in red. If we pull all of those onto the left-hand side, because we do not have any independent quantities, we just have i's, we now have 5r sub 1 plus 1 times I1 and then we have minus I sub 2 equaling 0. Questions on that?
Yeah. If you know, you have labeled in our circuit V sub 1 is across the resistor level. So if we know that to start with, can't we just plug in where our current source is right there? Can't we just plug in R sub 1, I sub 1?
So the question was, we could see by inspection, essentially, that V sub 1, which was given to us as far as where it is in our circuit, that is actually R sub 1, I sub 1. And so you could put that in there and replace V sub 1 with R sub 1, I sub 1. No, then you still, oh, I see, and then use the smaller meshes. No, you still can't use the smaller meshes because you still wouldn't know what the voltage drop across that was. You would have that dependent source in terms of your I's, but you still don't know, you know it as a current source. You don't know the voltage drop across it. So it's still a current source, and you would have to do the super mesh, but when it came time to writing that constraint equation to eliminate or to get rid of or re-express that current source in terms of your mesh currents, then you could use what you were just saying. You would say, oh, I have 5 times R sub 1, I sub 1 equaling I2 minus I1. Is that clear? But I would probably just keep it this way, and then at the end, I would say, oh, I have 5 V sub 1 equaling I2 minus I1. I need to get rid of V sub 1. Oh, it's clear. V1 is R1, I1. Let me use that now in that V sub 1 placeholder location. Question?
So on this example, does the second resistor take an effect at all?
So in this example, what is the purpose of R sub 2? Did it enter into any of our equations? Now I have to go back and look. It doesn't, because why? You now have a current source in there that's basically controlling I sub 1 and I sub 2, and R sub 2 is irrelevant. Now R sub 2 is not necessarily irrelevant in terms of the cost to operate this circuit. There's still current flowing through it, and if you put your fingers on it, it's getting hot. Something's happening. So it will be costing you something, but in terms of defining I sub 1 and I sub 2, it doesn't help you define, or I sub 1 and I sub 2 are independent of the value of R sub 2. So you could make that as big or as little as you wanted. What would you want to do if you were paying for the electric bill? You would want R sub 2 to be little. Correct? Maybe a line, a straight line, just get rid of it and short it out. Replace it with a wire and not a resistor. Question?
In the second equation, why is it that one of the terms is in terms of a voltage and then there's 2 just current terms? You multiply.
Okay, so now the question was, wait a minute, you've been telling me this whole lecture that you have to have consistency in your equations. Currents equal currents. And now you have a 5 V sub 1 equaling currents. What's up with that? Well, can't you see? Look at 5. Five has to actually have the units of currents over voltage. It's a scaling factor. It's hidden to you, but V1 is a voltage. That's a valid question. Very good question, actually. But 5, because it doesn't make any sense. But 5 has to have the units of a conversion factor of current or amps over volts, so that when it's multiplied by V1, you get amps. So yes, if you're checking your work and you go 5V1, uh-oh, I've done something wrong. Now you have to remember that that 5 is a magical 5. Okay? It's doing something special. It's special. 5. It's more than a 5. It's converting a voltage to current. Other questions? Yes?
Do you always assume the voltage across your resistors are positive no matter the orientation of your voltage sources?
So now the question was, are we always considering our voltage drops across the resistors? We're changing the direction of those voltage drops, aren't we, depending on which equation we're writing. We're trying to make those consistent with the direction that we're moving our currents or our paths around. So we're using the passive sign convention, and in this case, when we look at the first mesh, when we're going from left to right, that drop is consistent with the direction of I sub 1, and so our polarity, if we really wanted to label it, would be positive from left to right. So we don't really care so much about the polarity of the voltage. We just do it obeying the passive sign convention, and if we realize, or then we understand that as we're moving around mesh 1 or mesh 2, those polarities will take care of themselves if we write that particular drop consistent with the mesh we're on. Meaning if we're on mesh 1, I1 is always positive. And everything else, if we share it, and here's the if you're consistent with drawing your meshes in the same direction. If I drew I1 clockwise and I2 counterclockwise, that plus and minus stuff starts getting a little messy. But you could write it that way, it just is more difficult. Question? What's this business about superposition? Yes, I know, and I keep getting questions. Superposition. Here's the thing about superposition, because I can see the clock ticking. We need to do Thevenin and Norton's, which I'm going to maybe assume that you can spend your weekend, well, maybe not all your weekend, but most of your weekend doing Thevenin and Norton, superposition, and Wheatstone bridges. What? So superposition, here's superposition. If we, let's say, do I have a circuit? Maybe I do not have a circuit. So let me skip over Norton equivalence. Is that what I'm hearing? Thevenin and Norton, let me skip it for now and talk about superposition. Let me, what?
You're at the helm, Captain.
Okay. I'm not going to repeat that statement. You're the only one that thinks that. Superposition. What that means is in a linear system, a linear circuit, which is what we're dealing with, we are going to zero out all the sources but one and look at one at a time. And then we'll analyze the circuit with one source present and find the answer that we want. Then we'll say, okay, let's zero that one out and put in another one that is actually there. And look at the contribution from that source. Then we'll do another source. If you had 3 sources, you would turn one on, turn the other 2 off, and analyze that. I'm not going to do the other. Luckily, this is not on video. So then we do the third source and turn the other 2 off. And we look at the second source and turn it off. And I'm sorry, keep it on and turn the other 2 off. Get the voltage or current that we want with those 3 working independently and add those results up, and that's our superposition. So before I get into that, let me just talk about how we can shut things off. In superposition, what we are going to need is we are going to have to know how to zero sources. And that involves more than just holding fingers up and down. Meaning, if we have an independent, and these are independent sources, we can't zero out dependent sources. If we have an independent voltage source, and these ideas will actually be helpful in Thevenin and Norton, but we'll go back to that in a minute, maybe. If I wanted to zero out a voltage source, what does that mean? That means I want to make that source appear as if it has 0 volts across it. What do you know has 0 volts across it? A wire, a bare wire. So now if we want to zero an independent voltage source, we replace it with just a bare wire. We short it out. So we make them a pure short circuit. Pictorially, if we started with this, and we said, okay, zero that out, then what we're doing is we're replacing between here and here. That's a zeroed voltage source. Again, that's an independent source. It's not a diamond, it's a circle. If we are working with an independent current source, then if we have a current source and we want that current to be 0, we want no current to flow, what does that mean we have to do between my two hands? If that current source was here and it was putting something through that wire, how do we zero it? Now we open it up, don't we? We simply remove it, and then no current's going to flow. If we remove that, nothing's going to happen. That's how we zero current sources. So if we have an independent current source, then if we want to zero it, we open circuit them. Or pictorially, if we now have this picture, if it's going to be zeroed, that's how we do it. We simply open it up. That's how we are going to zero sources. Now let's see about superposition, because in superposition, we're going to just look at our sources one at a time. That means if we have 3 independent sources, we'll start with one being on and the other 2 off. We're zeroing the other 2, and we have to do something like this. Either if they're voltage sources, we short them. If they're current sources, we open them. And we just sequence that through, and then we sum up the answers that we get when each one was working individually. And that's superposition. We're superimposing those 3 results to get our total answer. That's what we mean by superposition. Let me see if I can write that down. In a linear system, and then we'll go through an example to help illustrate this, which are the circuits that we are going to be working on here. In a linear system or circuits, the response of interest. Now that's really vague, isn't it? But that's going to be some current or voltage. Let's say we're interested in some output voltage. Our response of interest is some output voltage. Then that particular voltage can be obtained by adding up all the response of interest contributions obtained for each independent source acting in isolation. Let me go through an example to hopefully make this a little more clear, and then maybe we'll open it up for questions. Okay? So let's, not that I'm discouraging questions, but I can see the time, and I want you to maybe do more than work this superposition problem over the weekend. And if we get through this example, maybe it will start to click, is my idea. So we want to find this output voltage using superposition. Here's the circuit. We have a V1. Let's say that that's 24 volts. Then we have a 2 ohm resistor. We have a current source, I sub I equaling 4 amps. We have another source, plus minus, let me call that V sub 2, and that's 4 volts. And we're interested in that output voltage across that 4 ohm resistor. Oh, and I didn't even label this top. Maybe I said it. This one's 2 ohms. What we want to do, so this is an example to illustrate the concept of superposition. How many independent sources do we have? 3. There are my 3 sources. What we are going to do is we are going to analyze this circuit 3 different times. The first time we will analyze it, we will keep V1 active. We'll leave it in place. We'll zero the other 2 sources. And we'll calculate what V0 is. We'll put that aside. Then we'll redraw the circuit with V1 0 and let's say V sub 2 zeroed, and we'll work it with just I sub I active, with the second source active, and we'll find V0 with just the second source active. And we'll keep that on the side. Then we'll zero V1, we'll zero I sub I, and we'll just keep V sub 2 active or on, and we'll find what V0 is when just V sub 2 is on. Now we have 3 different circuits that we've analyzed. They each give us some contribution in V0. We'll add those up algebraically, whatever those end up being, and that's going to be the actual V0 due to those 3 sources being present. We can do that because this is a linear circuit. If it was a nonlinear circuit, we couldn't use superposition. The circuits in this class are going to be linear circuits. We'll be able to use superposition. The reason we're doing that is sometimes by zeroing sources, it really simplifies the circuit or the analysis. And it might be easier to solve this 3 different times than try to solve this with mesh or nodal analysis. This one's not too hard to probably solve any of those ways, but I've just created it so that it will hopefully help illustrate what superposition is. Are there questions on the strategy? Because let's see how far we get. If I just keep V1 on, so now and I'm going to try to redraw this. let's say V1 is not equal to 0 and all the other sources are zeroed. What happens to my circuit? I now have this source, V1, is 24 volts. What happens to the current source? Or what happens to the resistor? The resistor, the horizontal resistor, what happens to it? It stays there. We're not changing that. That's still there. So that guy is still there. There's 2 ohms. What happens to this current source? We've zeroed it out. What does that mean? We need to just open circuit that. So now there is the current source zeroed out. There's no current flowing down through that branch. Then we go over and we hit the voltage source, V sub 2, but we want it to be zeroed. What happens to it? We zero that out, which means we short it out with a bare wire. And then we hit our vertical resistor of 4 ohms, and that's now V0. And you know what I'm going to do? Since we're doing this 3 different times, I'm going to put an extra subscript on that V0. I'm going to say that's V0 sub 1. Because I should be ending up with 3 different values for V0 associated with each of the 3 independent sources working by themselves. At the end, when I want V0, I'm going to add V0 1, V0 2, and V0 3, and that will be my answer. Right now I'm just getting the contribution due to one source, and that one source is V sub 1. Is everybody okay with that? What is the answer here? Or does this look like a fairly straightforward problem? You can solve this however you want, whichever way you feel comfortable solving it. If I were in your shoes, I would probably say, oh, that looks like a mesh. Or somebody might say, oh, wait a minute. That's one source, 2 resistors. That's a voltage divider. It's however you want to solve it. If you wrote mesh equations, you would put this current in there, let's say I sub 1. And if I use an I sub 1 later in other analysis, it's not the same I sub 1 in the next circuits. Or I could say, oh, this is I sub 1, 1. And then I would have a KVL. And that would be minus 24 plus 2I11 plus 4I11 equals 0. What's I11? Well, let me keep going. 6I11 is 24. Am I doing that right? Please stop me if I'm sleeping up here. What is then V sub 0, 1? Four times I11, which is 4 times 4, which is 16 volts. Does everybody see that? If you did it the other way, if you said, you know what, I see that as a voltage divider. I'm just dropping that original voltage of 24 volts across 2 resistors, which is really what you're doing, which maybe it's not clear from this. Oh boy. But that's all you're doing. You're dropping 24 volts across effectively 6 ohms. 4 here and 2 there. If we did a voltage divider, you don't have to do both of these, but you could if you were enjoying your Saturday evening and you enjoyed this. You could say, oh, V sub 0, 1 is, it's 4 divided by 2 plus 4 times 24. And this is 6, which will go into there 4 times, and there's 16 volts. We've checked our work. Is that okay? That's V sub 0, 1. We now have 2 more times to analyze this circuit. Let's look at the case when V2 is not equal to 0. If I sketch this circuit, is that picture correct? It would be if I had this labeled. There's 2. And if you always like to draw your mesh currents clockwise, there's nothing wrong with that. You could say there's an I1, 2. That's fine, if that's how you like to see these circuits analyzed. Doing that would allow me to say, okay, KVL now is 2I sub 1, 2 plus 4 times I sub 1, 2 equaling 0. Or 6I sub 1, 2 is equal to minus 4. Or I sub 1, 2 is minus 4 over 6, or minus 2/3. And what is now V sub 0, 2? It's positive in the direction that I have I sub 1, 2 flowing, isn't it? It's 4 times I sub 1, 2. That's 4 times, but I sub 1, 2 is actually negative. That's now minus 8/3 volts. That just means for that particular voltage source, it's wanting to make V naught negative. That's fine. That's just the way that source is working. Questions on that? Now we've analyzed it twice. Let's analyze it a third time. And now we want this current source to not be zeroed, but our voltage sources are zeroed. That means those become shorts. Here is I sub I, which is 4 amps. This is 2. And here is 4. Questions with how that's drawn? How do we analyze this guy? Do I draw meshes? You would have to do 2 meshes if you did meshes, right? You go, wait a minute. If I draw 2 meshes, I don't know the drop across that current source, do I? Darn it. So what else could I do? Well, I would probably, in your shoes, I would probably, until I get comfortable with this, I would say, you know what? I can stretch and contract these wires arbitrarily. Let me do this let me redraw this so it makes more sense to me intuitively, and I would maybe say, you know what? I can make that 2 ohm resistor actually over there, and I haven't changed anything electrically. Is that okay, that sketch? Do you see what I'm wanting to do? I'm wanting to say there's a node and here's a reference node. And let me call this node whatever I want it to be. Actually, it could be V sub 0, 3, correct? Is it possible now to write an equation in terms of V sub 0, 3? I can now write KCL. I now have this current, I have this current, and I have this current. What is the current on your left? Isn't it just the voltage drop divided by R, and that R is 2? What's the middle current? And all of these currents are leaving that top node, so I'm going to sum all of them and set it equal to 0. There's my middle current. That's given. That's an independent source. What about my current on the right? Questions on that? What is then, so now I have 1 over 2 plus 1 over 4 times V sub 0, 3 equaling minus 4. Or I have 3/4 V sub 0, 3 is equal to minus 4. Or V sub 0, 3 is now minus 16 over 3 volts. That current source is now wanting that voltage again to be negative. So two of my sources give me a negative output voltage. My first source gave me a positive. I can now find my actual output voltage. V naught is now V sub 0, 1 plus V sub 0, 2 plus V sub 0, 3, all by superposition. Now we've finished our supers. And this now becomes 16 minus 8 over 3 minus 16 over 3. That's V naught. That's now 16 minus 24 over 3, but that's just a difficult way to write 8. And V naught is 8 volts. Questions on that? Does that help or explain superposition? Have a good weekend. I will see you on Tuesday.